Hi everyone, welcome to the exercise portion of week 2 part 1 where we go over some of the exercises and their solutions. Okay, before I begin, it's really important that you try to do these exercises on your own before looking at this video. This is the best way to learn, and only once you get stuck, and by stuck I mean really stuck, that you've really tried hard, only then should you look at the solutions in this video. That's the best way to learn, and yeah, I trust that you will do that. Okay, so let's get to the first exercise. In algebra, 2x plus y is equal to 2x plus 2y. This is set here, this is called commuting. But you can't do this with logical symbols. You cannot commute the logical symbols. Let's see why by looking at the truth tables of the following statements. Now, what we're going to show is that not A or B is not equal to not A or not B, which seems like the intuitive thing that they'd be equal to each other, but in fact they're not, and let's see why. And just a note before we begin, not A or B is read as not A or not B, in the sense that it would be the same if I wrote not A in parentheses or not B. Okay, so let's start with A, not A or B. Okay, so the not here applies to the complex statement A or B. So as we've seen in the previous video, and I hope by now is someone familiar, we start with the most simple statements of this complex whole, and then slowly go towards the more and more complex. So remember that we start with A and B. These are the two simplest statements of our complex statement. And we have to look at all their possibilities. Now, A can be true or false, and B can be true or false, but there is a possibility where A is true and B is false, and vice versa. So we have to take that into account. So let's say A is true. There's two cases here, right? And B can be true or false. B can be true when A is true. B can be false when A is true. B can be true when A is false, and B can be false when A is false. Okay, so what do we do next? Well, since the not applies to the complex statement A or B, let's start with doing the truth table for A or B. Okay, so A or B. Now, do we have everything that we need to write the truth table for this? Well, yes, we do. We just need A and B and their possibilities. Now, if A is true and B is true, then A or B is true. If A is true and B is false, true or false is true. If A is false and B is true, same thing, it's true. And A or B is false if both disjuncts are false. Because remember, a disjunction is only false if all of the disjuncts are false. If even one of them is true, then the whole disjunction is true. Now let's look at not A or B, because now we have all the tools for it. So we can do not A or B. And this not applies to this whole statement, which we've drawn the truth table of. And so we're also ready to do it. So what is not of true? Well, not true is false. Not true is false. Not true is again false. And not false is true. Okay, so we've done the truth table. We're actually done here. Let's move on to part B, which is not A or not B. Now, it seems like it's tedious, but let's just do A and B again, because that will make our lives easier. So let's go through all the possibilities. So A can be true or false, B can be true or false. And okay, so what is the complex statement in this case that we care about? Well, or applies to not the disjuncts of or are not A and not B. So actually, we should do these first, not A and not B. We should figure out what their truth values are. Okay, so not A, if A is true, then not A is false. If A is true, not A is false. And same thing, if A is false, then not A is true. and same thing for the last row. Okay, now we do the same thing for not B. Okay, so here we look at this column over here. So if B is true, then not B is false. If B is false, then not B is true. If B is true, then not B is false. And if B is false, then not B is true. Okay, are we done? Well, not yet, because we haven't done the most complex logical operator, which is OR here, which applies to not A and not B. And so let's do that one. So what about not A or not B? Well, here we'll look at the disjunct between these two columns. So what false or false over here in the first row, false or false is false. False or true is true. True or false is true, and true is true. Now we can ask, are these two the same? Are they equal to each other? Well, no, you see that they don't have the same truth value in all the same cases. If A and B is true, if both of them are true, then not A or B is false. Sorry about that. All right, in this first row, we have false. If we look at the first row here, when A and B are true, then not A or not B is false. Okay, so here actually they agree. But what about the other ones? What about the second column? Let's look. If A is true and B is false, then not A or B is false. If A is true and B is false, then not A or not B is true. So we see that these are not the same. So they differ. So they're not equal. The same thing holds for this third column. They're not equal. Whereas in the fourth column, when A and B are both false, then they do have the same value. But since they differ in both the second and the third row, then we know that they're not equal. Okay, so I hope to have convinced you that the logical operators aren't commutable. Okay, we can now tackle the second exercise. In this exercise, I give you two definitions, and then you're asked to figure out which of these statements satisfy these definitions. So the first definition is of a tautology. Tautology is a statement that is always true, and a contradiction is kind of the opposite of the tautology, and it's a statement that is always false. So which of these statements are tautology, which are contradictions, and which are neither? Okay, so let's look at these two together, because we see that there's only A here in exercises little a and little b. So let's draw the truth tables. That's the easiest way to see when if they're always true or always false. So, right, we have A over here, and we don't have B. So we just have to consider cases where A is true or false. These are the only two possibilities. Okay, so the next most complex part of these statements is not A, right? We see not A over here and not A over here. And the logical operators or and, these apply to A and not A, similar over here. So the simplest one is not A. Okay, so if A is true, then not A is false. And if A is false, then not A is true. Okay, so we're done. Now we can do both of the complex statements, A or not A, and we can also do A and not A. All right, so A or not A. So if A is true, then not A is false. And if we take the disjunction over here, true or false, then this is going to be true, right? A disjunction is only false if all of the disjuncts are false. And similarly over here, we have a case when false or true is also true. Let's do the other one, A and not A. So remember then a conjunction is false if even one of its one of the conjuncts is false. And here we have one of the conjuncts being false over here with not A, and one of the conjuncts being false with A in the second row, so it's going to be false and false. Okay, so now we can answer the question, are A and B either tautologies, contradictions, or neither? I'll take a minute to think about it. But A or not A is a tautology, so we put taut over here, because it's always true. There's not a single case where A or not A is false. And similarly, A or not A is, A and A is a contradiction, because it's always false. There's not a single case where they are not, where it's true. Okay, we've seen that A or not A is a tautology, and that A and not A is a contradiction. Now let's go to C, D, and E, which are a little bit more complicated because they don't just have A as the simplest statement, but they also have B. So before we even start, we can just set everything up with our truth tables of A and B and all the possibilities. So again, A can be true or false, and A can be true, and B can be true or false. And here we've exhausted all the possibilities. Either they're both true, they're both false, or one of them is true and the other is false. Okay, let's look at C, A or B. We've done this in the previous exercise, so A or B. Let's just do it again. True or true is true, true or false is true, false or true is true, and false is false. Is C a tautology or a contradiction? Well, let's see. Is it always true? Well, no, it's true in the first three rows, but not in the last one. And is A or B a contradiction? Well, no, because it's true in the first three rows. So A or B is neither. Okay, what about not A or B? So here we take not the complex statement A or B, and we just, before we even do the truth table, you might already have a sense of whether it's true or it's a tautology or a contradiction. Since we're doing not of this statement over here, what's going to happen is that the truth values are going to switch, but they're going to switch in a sense symmetrically, so it's going to be false, 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 true. And so there's going to be this, right before there were three trues, and now there's three falses, and before there was one false, and now there's one true. So it's still the case that this is neither, that not A or B is neither a tautology or a contradiction, because there's a case where not A or B is true, and there are many cases where not A or B is false. So it doesn't satisfy the definitions. Okay, what about not A and B? So here we don't need to draw another whole other truth table. We just draw the truth values for A and B, but here we have to go again to the first and second column. So true and true is true, true and false is false, false and true is false, and false is false. Now, is this a tautology or contradiction? No, it's neither, but what we care about is not A and B. And this is again just going to flip these truth values to false, true, 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 because we're taking not of this column over here. And so it's also not going to be a tautology or a contradiction. So it's neither. Okay, and we're done for this exercise. Now we can look at exercise number 3, which is taken from Choice and Chance of Brian Skirms, the textbook that we're reading in the class, or one of them. And it asks, check the following arguments for validity using truth tables. Okay, so let's start with number A. P, therefore, P and P. Now, we can again do the truth tables here, right? We only have to deal with P, so it's true or false. And let's look at P and P. And if P is true, right, P and P is going to be true, right? True and true is true. And if P is false, then P and P is going to be false. So let's put this in argument form, kind of how we've seen. P, therefore P and P. So you can ask yourself, is it possible, right? Let's take a step back. To check for validity, we need to check, is the conclusion guaranteed to be true if the premises are assumed to be true? Okay, now here, there's only one case where we have that the premise is true, which is in this row, in which P is true, right? That's the premise. Let's assume that P is true. Is it possible for P and not P to be false? Well, there's no case where that happens, so it is valid. So when P is true, P and P is always true. Another way to look at it is to say, let's assume that the conclusion is false and look at whether the premises can be true. So here we'd look over here, P and P, let's assume that it's false. Is there a case where the premise is true? Well, no, the premise is false there. So here, this is valid. All right, so we've seen that little a is valid. Let's look at little b. And you might already get the sense that this is also going to be valid, because let's look at the argument, P, therefore P or P. Right? We can look at this even before drawing the truth table. Is it possible for the premise to be true and the conclusion false? Well, it doesn't seem so, right? And let's prove that using the truth tables. So again, P can be true or false. And let's draw P or P. And so if P is true, true or true is true. And if P is false, then false or false is false. So the same situation as before. If we assume, let's assume P is true, then we have to go to the row or the rows where P is true and see, is it possible for the conclusion to be false? Well, no, because we see that the conclusion is true here. And that's the only case, so it's valid. Okay, now let's look at a slightly more complicated case. The argument is P or Q, therefore P. Right. Let's draw this in our argument form. So P or Q, therefore P. Now you might imagine this in concrete statements. For example, Piper is a dog, or the sky is green. Therefore, Piper is a dog. Intuitively, you might already sense that there might be something fishy here. So the first thing to do is again draw the truth tables. And we do the same way where we start with the simplest statements and then go to the more complicated statements. All right, so P and Q, right? Now it's more complicated than the first cases. We have 4 possibilities, right? They might both be true. You have 2 cases when one is true and one is false, or they might both be false. And then we draw the table for P or Q. True or true is true, true or false is true, false or true is true, and false is false. Okay, so now let's look at cases where we have to assume that P or Q is true. So those are the rows of the truth table that we're going to look at, because remember the first step is assume that the premises are true. all the premises, that is, but we only have one here. So what are the rows in which the premises are true? Well, actually, the premise is P or Q over here, and in this row it's true, right? In the second row it's true, and in the third row it's true. And now we have to say, okay, are there cases where the premises are true, but the conclusion is false? And if there are, then the argument is not valid because it's not guaranteed. The conclusion is not guaranteed by the truth of the premises. Okay, so let's look at the first row. Well, P is true here, that's the conclusion, so everything's good. P is true in the second row, so everything's good. However, on this third row, you might notice that we have a possibility where P or Q is true and P is false. So it is possible for this to be true, for the premise to be true, and the conclusion false, so this is not valid. It is invalid. Okay, now let's go to our last case where it's P and Q, therefore P. So let's quickly just do P and Q again, right? These are the simple statements and should come rather quickly. So true, true, false, false, true, false, true, false. Right, and drawing the P and Q is going to be also easy. True and true is true, and in all the other cases, it's false. Okay, so let's do it again. P and Q, therefore P. Sorry, my pen is acting up, but okay, so is it possible for the premises to be true, but the conclusion false? Well, again, assume premises are true. We're going to look at cases in the truth table where that's the case. Well, we only have one case, right? All the others, one possibility. All the others, P and Q is false. Okay, so is it possible for P and Q to be true and P to be false? Well, no, because P in this case is true, so we're good and the argument is valid. And we're done. Okay, so let's get to the last exercise, which I think is the most challenging and requires you perhaps to make a few steps of critical thinking. So, is an argument that has P or not P as its conclusion always valid? Why or why not? So if you haven't done this, again, pause the video and try to think, because there's a few steps here. So what would make an argument always valid? Well, go back to the definition. It means that the truth of the conclusion is always guaranteed given the truth of the premises. Okay, and so here I'm just telling you something about the conclusion. So P or not P is perhaps, as you might remember, a special type of conclusion. P or not P, as we saw before, is a tautology, meaning it is always true. Okay, so suppose we have an argument and I give you, say, a premise, a premise, a premise, and then I have P or not P as the conclusion. Now, you might notice, well, the conclusion is always true, no matter what the premises are. And so, it's always guaranteed to be true. If it's always guaranteed to be true, then it's always guaranteed to be true given that the premises are true. Okay, so actually, this is a case where P or not P is always guaranteed to be true, so the argument is always valid because it's a tautology. Now this is kind of a degenerate case, right? If I tell you Piper is a dog, therefore the sky is blue, or the sky is not blue, then there's something weird about it. But that's just how it is. Sometimes when you build these systems, you get kind of what you might think of degenerate cases. So arguments in which the conclusion is a tautology, they're always valid. Okay, so now we're done. I hope you've enjoyed doing these exercises, and I hope they help you to do the homework.